Welcome to this tutorial on matrices and matrix operations with SymPy. We'll start this video with a vocabulary overview to get on the same page, and then we'll discuss how to make matrices and vectors in SymPy and store them into variables. We'll talk about doing operations with matrices, some of the special matrices that SymPy offers built in, and then we will close with accessing elements, rows, and columns of a matrix with index expressions. Note that for this video, I am running SymPy from my web browser at cocalc.com, and that has SymPy already pre-installed. But what we go through today will work just as well if you're using SymPy downloaded onto your machine using something like PyCharm or what have you. And downloading instructions for SymPy can be found on SymPy's website, the link to which is in the description, or you can generally just put in your terminal pip install SymPy and it'll work. If that doesn't make sense, just again, the instructions will be on SymPy's website. But first, some quick vocab before we jump into how to do all this in SymPy. A matrix, I might not revisit all of these terms in this video, but I do want to run through them. A matrix is a rectangular array of numbers in rows and columns. The numbers inside a matrix are each called an element, so like this 23 is an element of the matrix. Oh, sometimes you'll hear me say the order of the matrix, that's rows by columns. So the above matrix here, this is of the order 3 by 4 because there are 1, 2, 3 rows and 1, 2, 3, 4 columns. So it's a 3 by 4 matrix. And then we just talked about element. A vector is a matrix with only one row or only one column. So this is a vector that's only one row versus this would be a vector that's only one column. And a scalar is a matrix with the order 1 by 1. It's just one, one element as a matrix. So you'll hear me saying some of these words. Just wanted to make those clear. So how do we make a matrix in SymPy? Let's go ahead and delete this out because we won't need it, and I can just do that with dd. All right, so first things first, let's import the matrix object and some symbols. If you're not sure how to do this, please do take a look at my intro to SymPy video, and we'll put a link into the description for that. But let's go ahead and do from sympy.matrices, okay, import matrix. And now note there's a capital M, and now every time we're going to make a matrix, we'll just write matrix. I could have done import SymPy, and then we would do sympy.matrix, but since we're only using a few things, we'll just do it this way. From sympy.matrices, import matrix with a capital M. And let's go ahead and import some symbols that we're going to work with today, and we can do that. One way to do that is from sympy.abc import x, comma, y, comma, z. And that's, we could have used any letters here, but those are the symbols that we'll use today. And we'll go ahead and run this cell with Shift Enter or Shift Return if you're on a Mac, and that's how you run the cell in a Jupyter notebook. And that will import both the matrix and some symbols for us to work with, though we won't be doing too much with symbols. So the function matrix, that's matrix with a capital M and parentheses, and inside these parentheses you can put a few things to make a matrix. The first way that we'll do this is we can put inside these parentheses a set of brackets, which is what the matrix will go into. And then inside these brackets, we can put each individual row of our matrix, okay, in each of which is inside another set of brackets. So we'll have, for example, 1, 2, comma, and that'll be one row of the matrix. Another set of brackets for, say, just 3, 4, comma, another set of brackets 4, 5, 6. Okay, so that's 1, 2, 3, 4, 5, 6. So that'll be row 1, row 2, and row 3, all one on top of the other. See how it looks. And there it is. There's our matrix. You see it is a 1, 2, 3 by 1, 2. It's a 3 by 2 matrix of these elements here. What if we wanted symbols in our matrix instead? It's no problem. Remember, we imported symbols x, y, and z up here, so you can certainly do something like matrix 1 comma x, y plus x comma z, and 5 comma 7, or what have you. Okay, and if I run this, whoops, well, I made the very thing that is not intuitive, but it's a good thing that happened because you see what happens. You need this outer layer of brackets. Okay, so so you need the outer layer of brackets and then each of these inside its own inner layer of brackets, each row inside its own set of brackets. So what do we have here? We have a matrix and it has symbols, it has an expression. It all works just fine. If you're confused by the symbols, again, just look at the introductory video. You may recall you can substitute in symbols in SymPy expressions. That's just as true with matrices. Just end it with dot subs, and you can substitute in. So let's go ahead and copy this and paste it into a new matrix, or a new cell. And you can do dot subs, and then x comma, say, 42. And then all of a sudden, as you'll see, every time that we had x in this matrix, you can run the cell. And every time we had x in this matrix, now it is instead the number 42. And that's just dot subs, x42, so the symbol that you want to substitute, and then whatever you're substituting it for. Another way to make a matrix that is different from this first formatting where it's row by row by row, you can also make a matrix as such with matrix where you put the order. So remember, this is a 3 by 2 matrix, so that's 1, 2, 3, 1, 2. So you can put the order, a 3 by 2 matrix, and then all of the elements of your matrix just in a list. And so remember, this was 1 through 6. So you would do 1, 2, 3, 4, 5, 6. And if you run that, you'll see it's the same exact matrix that you had before. It's just that, rather than splitting it out 1, 2, 3, 4, 5, 6, you say, hey, here's the order of the matrix that I want. I want it to be a 3 by 2 matrix. And here's all the elements. And then you let SymPy do the work for you of arranging those into the rows and columns. And so there's advantages and disadvantages here. The advantage is that you can change it up without going back and redoing all the brackets. So if you wanted a 2 by 3 matrix instead, you can just do 2 comma 3, and it will automatically change it to a 2 by 3 matrix. So that's nice. Versus if you had wanted to do that up there with that format, you would have had to type it all out again. And the disadvantage, though, is that you have to somewhat know in advance what the order of your matrix will be, because if you put in some order that won't work with these numbers, then you're just going to get an error. If you want to make a vector that is a matrix of just one row or just one column, you can certainly do so, and I'll show you a couple of ways to do that. Let's just empty out some of this junk. Okay, so you can certainly do that. Let's go ahead and do matrix, and if you do just one bracket here, 1, 2, 3, 4, you can think of this as the format we saw just now, where there was an order and then comma and then just one list, but we're not putting in any order. It's kind of leaving that blank, and it's just going to give you a vector. And in this instance, it's going to default to a column. So you see it's just a column, 1, 2, 3, 4. 1, 2, 3, 4. That's just the default way it is. You could if you wanted to give it more detailed instructions, such as saying, no, I want this to be a 1 by 4 matrix, you can, of course, do that. 1, comma 4. And now all of a sudden it's a 1 by 4 matrix, or a vector, a row vector, that has 1 row and 4 columns. So you can certainly do that. Another way that you can do this, though, is you can do the vector as if it was that first one we saw where there was a bracket, and then inside the bracket was each row that you wanted separated by columns. So 1, 2, 3, 4. And then here's where you would put like comma, 5, 6, 7, 8 or whatever. But don't do that. If you just have just this and you run it, 1, 2, 3, 4, because remember, this is just the first row in what could be future, more rows later, but it's just the one row, and that's just going to give you a row vector. You can also transpose a matrix in a couple of ways, and that is one way that you can quickly turn a row into a column and vice versa. So you can do that with a dot t, or you can do it with a dot transpose with parentheses at the end. And either way will work. Okay, so you can always flip your row to a column or column to a row with transpose, and it'll also work on a bigger matrix. It'll transpose the whole matrix. All right, so we've seen matrices that are just in cells. I mean, that's fine. That and a nickel will get you a cup of coffee, right? But how do we store the matrix that we made and use it later? Well, we can store it inside of a variable, just like you can with numbers, strings, or any other data in Python. And a commonplace notation that you'll see in mathematics is to assign a capital letter to denote a matrix, so A. And don't feel beholden. You can certainly give it a more descriptive name than that. It'll work out just as well. But you're probably going to commonly see something like this, where it's like a capital A, and then you can just put in your matrix. So I'm gonna copy paste in a matrix that I've pre-written because we're going to use it a lot later. But just to show you, remember I have my outer layer of brackets, and then I have each row inside its own set of brackets. So in this case, I've got a row that's 8720, comma, a new row, right, 973.23.1, comma, and then my third row, right? And if I run it, it's not going to display it like it did before. It's just going to store it. It's just going to store it inside that variable A. And if I want to display it, I could certainly do so like that with A, just by running it. And that's because the Jupyter Notebook is always going to give the last line outputted. If I have like a 2 plus 2 here or something, though, remember the Jupyter Notebook, it's not going to know that I also want to display the A. There's a couple of ways you can get around that if you want to display both of these things. One, if you just want a normal kind of printing, and where it's just going to give it as like, hey, it's basically just going to print this back at me, this matrix statement. You can just do print like you would in Python. Or you can also, if you want to, from SymPy import p print, okay, and that's like a pretty printing, p print, and then when you run it, you need to actually do it. You can do p print a, and then it'll pretty print it, with the best possible printer, which in CoCalc is this nice latex printing. If you're following along on like PyCharm or something, it's going to look a little different, but it'll still look pretty good. And so pprint is just a way to display it. Though I don't think it's going to come up again in this tutorial, but it's still something I wanted to show you. So anyway, if you have A, you can see there it is. There's your matrix stored inside the variable A. So that's great. Notice that I have notice that I've used this particular method of row by row. That was just arbitrary. The other method would have worked just fine, where you put in the order and then just list it out. And so I'm going to go ahead and make a second matrix with that method called B. And so B equals this matrix. It's going to be a 3 by 4 matrix. and it's going to have these numbers in it that SymPy will then arrange to be a 3x4 matrix. So if I run this, and then if I want to run B, I will see it. Okay, and so now I have stored inside this variable B this matrix. Okay, this sets 4, 6, 8, 1, etc. So now that we have two matrices, let's talk operations. You can do lots of different operations with matrices very easily just by using your variables as a stand-in for the matrices. You can certainly write out this whole matrix and then plus and then write out that whole matrix, but that would be very ungainly. It's much easier to store them into variables and then do operations from there. So actually there we go. So, for example, if I were to do A plus B, what would that mean in the world of matrices? Well, let's take a look at this image. If we just add A plus B, and here's my matrix A, and here's my matrix B that we've just seen, all it's going to do is it's going to take it and add each one to the corresponding element. So 8 plus 4, right? 7 plus 6, 8 plus 2, okay? I guess it probably should have been written as 2 plus 8, but even so, 2 plus 8, 0 plus 1, okay? It's all going to just add together, and you'll end up with this 12, 13, 10, 1, and all the way down the line until you get to 29 plus negative 93, 29 minus 93 for negative 64. Let's see how well it works. A plus B, and there it is, 12, 13, 10, 1, okay, all the way down to the negative 64. It just added each of these elements to their corresponding element in the matrix. So one thing that you might have noticed, though, is that because you're just adding or subtracting each element to its corresponding element, it has to have a corresponding element, which means your matrices have to be of the same order. That is to say, they have to have the same size of rows by columns, or it won't work. You're just gonna, get an error. It won't work. All right, now let's take a look at multiplying matrices, which is a little more complicated. There's a few different ways to talk about multiplication when we talk about matrices. One way is this just multiply everything in the matrix by the same number. Okay, so for example, if you have 3 times, your matrix, I believe this is matrix B. Yes. And so if you have 3 times matrix B, it's just going to go 3 times 4, 3 times 6, 3 times 8, and it's just going to multiply that 1. And this is if, you're multiplying a scalar or just, one number by the matrix. It'll do it for each element. Let's see it in action in a couple of ways. So for example, you can do 3 times B, and there it is, and it should be exactly what we saw here, the 12 all the way through to the negative 279, and it is. You can also, of course, do, because of SymPy, you can do symbols with these operations. So if I were to multiply x to the power of 3 times b, okay, so now I'm multiplying b by each element in b by this symbol x cubed. What happens? Works just fine. You end up with each of these elements in B, okay, 4 all the way to negative 93 here, and they are each multiplied by x cubed. Second, you can do what's called element-wise multiplication. So this, for example, is where you have say you have A and B again, and they're the same order, and you just multiply element-wise. You multiply element by element. 8 times 4, 6 times 7, just the same thing that we saw with the addition and subtraction. Well, that's not true quote-unquote multiplication of matrices, which we'll see in a second. So you can't just use the star symbol for multiplication, because you're not really multiplying the matrix by the matrix. You're doing something a little different, element-wise multiplication. And so for that, you need a special function, and there's a couple that you can do. You can either do A dot multiply element-wise B, or you can import a function called multiply element-wise, and then the two arguments will be A and B, with the one that you want to multiply by the other one. So let's see it in action. So first, you can do A dot multiply underscore elementwise B, and that did it. Okay, we got our, each element multiplied by its corresponding element. Or if we had up here imported multiply element-wise, normally you do this at the beginning, but because this is, so actually the function is called, when it's a function, matrix underscore multiply underscore element-wise. So you would import, you would include in your from SymPy import matrix underscore multiply underscore element-wise. And then, because we just re-imported everything, let's make sure we're saving our variables by running the cells with A and B in them. And now let's go back down here. Now, remember before we had A dot multiply element-wise B. The other way to do this is with matrix underscore multiply element-wise parentheses A comma B. And there it is, and you see it's the same result. So that's just a function that you can import from SymPy. Don't forget the matrix like like I did. It's actually a little different from what you would put if you were doing it this way, which is A dot multiply element-wise B, but either way will work. But the key takeaway, though, is that it won't work if you're just doing A times B. And that's because the third type of matrix multiplication, which is a little bit more that I want to talk about today, which is a little bit more complex, is to multiply two matrices together, A times B. And so as you'll see in this picture, we have, what I'll call B, though bear in mind this is not the same matrix that we've been calling B, but that's okay. And there's a good reason for that, as we'll see. So we have these two matrices we want to multiply together, A and B, that we need to take, so in order to do that, we'll need to take each element in the first row of A and multiply it by each element in the first column of B, and then add all those together. And that's all just to get the first element of our new matrix. So you see we have 8, all right, times 4, okay, 8 times 4 plus 7 times 483 plus 2 times 19 plus 0 times 11. Add all those up together and you get 3,451 just for the first row and column, like the first element of the matrix. It took all that work, and you see it goes and goes and goes, so this would be very tedious to do by hand, but fortunately we do not have to do it by hand. So this other matrix, we're just going to store it into a new variable. I have it here, so I'm going to copy and paste it, and we are going to store this into our new variable C. So this is a 4 by 3 matrix, 4, comma 3, comma, and then we list out the numbers in the matrix. If you want to type along by home, you can. This is 4, 6, 8, 483, 39, negative 3, negative 19, 4, 1, 11, 0, and negative 42. And so all you do is you run the cell to store that in. Why does it have to be a 4 by 3 matrix? Well, if we go back up here, you will see that the columns in the first matrix have to equal the rows in the second matrix, and that makes sense if you think about how the operation works. So before, while we had all of those, equal order matrix, all these 3 by 2 matrices plus another 3 by 2 matrix or something, and that's how that would work because it's element by element. Here, the multiplication is totally different. It's a matter of the columns in the first matrix have to equal the rows in the second matrix. So we have C, it's stored, and so now let's do A times C, and we run it, and were we right? Yeah, so 3,541 all the way to negative 1607 looks great. One note, matrices are not commutative. A times C does not equal C times A. If I were to do C times A here, it would give me something completely different. And that makes sense if you think about how that operation worked. So unlike, normal things where it's like, oh, 2 times 3 is the same as 3 times 2, doesn't work here where A times C is not going to be C times A. Also note that you can certainly have symbols here. So if for C, instead, actually, let's make a new one and call it D. So say we had D here, and our matrix, say instead of this negative 3, we had, an X, and instead of this 11, we had Z plus Y, and we ran that. So you can certainly do A times C, should still, oh well, yeah, A times C, A times D should still work just fine. And you see you have some expressions, you know now that you have some symbolic, items. And of course, as before, you can substitute in anything you want for the X or the Y or the Z. It'll all work just fine. All right, so SymPy also has a number of built-in special matrices, so let's go ahead and run through some of those. I'm going to just delete out some of this. Okay, and we'll make some new space. All right, so special matrices. The first thing that we want to do is we want to import any special matrices that we want to use. So these are imported in the from the SymPy.matrices. Okay, so from this line, all you have to do is import them. The ones that we're going to be seeing today, though there are many, the ones that we'll be seeing today are ones, zeros, I, that's EYE, and RAND capital M matrix, RAND matrix. All right, and so let's go ahead and run this to import. And let's remember, because I think we're going to come back to A and B, so let's go ahead and run those now, just so we have them stored again. All right, so now let's go ahead and do these each in their own cell. So we had ones, we had zeros, EYE, and RAND matrix. Now, when we feed in arguments, let's go ahead and put in 2, 3 for each of these, except for the I, which is the identity matrix. That one, let's keep a square matrix, and you'll see why. So let's put in a 5. But for the rest, let's go ahead and put in 2, 3, and then we'll run these one by one, and we'll see what happens. So when we run this one, you'll see we have a 2 by 3 matrix, 2, 3, 2 rows, 3 columns, all of ones. Same with the zeros. It's going to be all zeros. The identity matrix here, the one where I did not want to put in order, okay, instead I wanted to make it a square matrix, so I only put in a 5. It gives you this 5, 5, 5 matrix with a nice diagonal of ones. By the way, if you wanted a square matrix with these, you can just put in one argument and it'll give you a square matrix, a 3 by 3 of zeros, for example, here. But the I matrix, the identity matrix, the secret to its success is this diagonal of ones. So you know how like any number times 1 is that, so like 3 times 1 is 3, and so you would say 1 is the identity. So that's what this is, but for matrices, it's the identity. And the diagonal of ones is kind of what makes it work well, and so, that's why I kept it a square matrix. If we do like 5, 9 here or something, it'll still spit out something for you. It'll just have that diagonal of ones and then everything else is a 0 because it would have continued with more ones down here if it were big enough, if it had enough rows, but it doesn't, and so it just has kind of this thing. but you'll generally see the identity matrix as a square matrix, so it has that nice diagonal. And finally, the random matrix. If we do this rand matrix 2 by 3, let's run it. You'll see it gives us a 2 by 3 matrix of random integers. I believe the default min and max is 0 and 99, but you can change the minimum and maximum value that you want it to pull from with some keyword arguments. So if you do comma, min equals 11 and max equals 14. All right, so those are keyword arguments. So comma, min equals 11, max equals 14. And if you ran that, now all of a sudden you're looking at a random matrix where there's a minimum value of 11 and a maximum value of 14. And that should be inclusive. Let's run it a couple of times. Yeah, so it is inclusive. So a minimum value of 11, a maximum value of 14, inclusive of the 14. And so if you were filming, and you can do this with anything, right? So you can do any range of values here. So just for example, a normal use case of this would be if you're filming a cool movie about hackers and you wanted to make a cool graphic. So you would do random matrix 0, 1. So you get kind of the, no, I'm sorry, random matrix of 500, 10. So you would get 500 rows of 10 columns, and then with a minimum value of 0 and a maximum value of 1. And this will generate for you this pseudo-random, zero matrix of zeros and ones. So if you run it, right, and just give it a second because it's 500 rows, it'll take a second. All right, and there it is. Okay, and so now let's scroll up here. There we go. And what you can do with something like this, where it's this long list, is you can just kind of scroll down it while the dramatic music is playing, and then and then you shoot to the hero. He takes off his sunglasses. He says, "I'm in," and there it goes. Now it's scrolling. Okay, and then he says, "I'm in," and the other hacker friends say, "Wow, you're such a good hacker," and that's how you that's the most practical and useful way to use. No, I'm kidding, of course, but that does demonstrate how how you can generate the matrix, the random matrix that you want. I'm just being silly though. Okay, and the last thing I want to go into is accessing elements of a matrix. Let's go back into our matrix A. And we have our matrix A. So recall that in Python you start counting elements of a list at 0. That's also true with matrices in SymPy. They keep that convention. So it's a little unintuitive, but you can think of this 8 in the matrix in the top left corners kind of having the coordinate 0, 0 when referencing the elements of the matrix. Python and thus SymPy starts counting at 0. So if we wanted to pull the number from what we humans would think of as the second row, third column, this 23, the computer would not think of this as 2, 3. It would actually think of this as 1, 2, right? Because you have 0, 1, that's column number 1, and 0, 1, 2, column numbered 2, because you're starting at 0. So if you have A, and then in brackets, you put in the think of like the coordinates of what you want, right? If you put in 1, 2, so that's row number 1, starting at 0, 0, 0, 1, 2, 0, 1, 2, you're going to end up with this 23. And there it is, your 23. Okay. And if you did what would be more natural seeming, and you had put in 2, 3 here, it's not going to get you what you want. It gives you the 29 because remember 0, 1, 2, 0, 1, 2, 3. That's the 29. Okay, 2, 3. You can also use a colon to access a swath of the matrix. So if you do, for example, A and then in brackets, and the first number, instead of a number, you put a range, 0 to 3, comma, and then and so that would be for row, and then for column, you put in, actually, let's do 0:2 for row, and then put in 0:3 for column. What's it going to give you? It gives you this. What is this? It gives you this 872 and 973.23. Notice that what's after your colon here is not inclusive, so it gives you, basically row 0 and 1 and column 0, 1, and 2, because it's not inclusive of the 2, it's not inclusive of the 3. So that's just another tricky thing, and that's just from Python syntax. So if you're not sure what I'm talking about here, you can just look at there's lots of guides and things on indexing lists in Python, and it's the same kind of principle. So say you wanted just the 773 and 2 columns, 773 and 2. There's a few ways to do it. One way is you can use a and then 0:3, 1, right? Because you want, so you want the 773 and 2, so you want row 0, 1, and 2. So that would be 0:3 because you're not including the 2. And then you only want column 1, 0, 1. So 773 and 2. So say you do that, and there it is. Okay, so that's one way to do it. You could also access individual rows or columns with its own syntax. If you do a.row, you can actually pick the number of the row you want. So if you put in like a 2, what's this give you? That gives you row number 2, which is 0, 1, 2, the negative 48 through 29 here. Gives you the whole row. Or if you want just the column, it's a.col. And if you do 1, because remember 0, 1, and that'll give you the 773 and 2 as well. And there it is. Okay, so that concludes our video on matrices with SymPy. I hope you got value out of this video. If you did, please do show your support by giving it a like. It makes a difference. There should be more SymPy content coming, so if you're interested in that, I'd ask that you subscribe as well. And thank you very much for watching.